Hello, everyone. My name is Ryan Hill, and I'm a software engineer who has been working on ONNX Runtime since it started about 4 years ago. So what is ONNX Runtime? I figure many of you will already be familiar, but for those who are not, it is a runtime for ONNX models. It is cross-platform, can target multiple CPU architectures for all major platforms, and has language bindings for many current programming languages. Currently, we're doing releases roughly quarterly. Who uses ONNX Runtime? At Microsoft, it's used across all of our major product groups like Windows, Office, Teams, Azure Cognitive Services, and VS Code. We have over 160 models in production with a rough ONNX Runtime is also widely used outside of Microsoft across various industries, with a handful of companies shown here and a few of which you'll also hear from today. We continue working on improvement with each release and features evolve as new models and scenarios come up from our users. Here are a few notable new features to call out from the last couple of releases. One is that we added new APIs to allow op kernels to be called directly from outside of a model run call so that they can be used like a math library. We had users adding custom ops that extended an existing op, and they would copy the internal code for the op and then add a relatively small change around it. Now they can just call the ops directly. We also added the ability to feed external initializers as byte arrays for model inferencing. This is useful for large models. Previously, this required a file on disk, but now can be done entirely in memory. Performance continues to be one of the key priorities for us, as we support many large-scale, high-volume production workloads. Here are some performance improvements that you get for free just by updating to the latest version. In 1.10, we added a transpose optimizer to push and cancel transpose ops, significantly improving performance for models requiring layout transformation. In investigating some performance numbers, we noticed we could optimize away some heap allocations by doing a small size optimization in our op kernel code to handle shapes, and in related code using shape size standard vector classes. So now instead of using standard vector, we use our optimized tensor shape and inline vector classes. And then, so instead of doing a heap allocation on every instantiation, they're now only done in rare cases involving shapes with larger than normal numbers of dimensions. To give an idea of the improvement, one test showed a drop of 70 heap allocations down to just 6 on each run. And another team saw their performance improve by around 100 microseconds, going from 479 down to 360 microseconds. Quantization has also made some nice improvements. You can see here a bunch of common CNN-based models running up to 50% faster in the latest version. Execution providers are how we enable ONNX Runtime to perform its best on today's various hardware possibilities. Some providers are just ONNX Runtime code implementing kernel ops using a hardware API, like CUDA, and others are using a software library that already implements the op math optimally using a particular hardware API, like the TensorRT library, which uses CUDA, and OpenVINO using various Intel hardware. So why not just use a library like TensorRT directly? Well, for running models, ONNX Runtime offers a single API that gives you the flexibility to run on almost any target hardware optimally with very low overhead. And ONNX Runtime has a complete CPU implementation. So if something isn't supported in a provider, it will fall back to the CPU version. In developing these providers, our engineers work together with the outside company engineers to ensure the best results and to create an ongoing relationship where everyone benefits. As you can see, as these hardware APIs and libraries continue to be updated, we continue to update our providers along with them to ensure that we maintain top performance and the latest hardware support. We saw the need for a performant, low-footprint model inferencing solution on mobile devices and released the ONNX Runtime mobile packages about a year ago. Since then, we've continued to invest in these platforms to improve usability for mobile developers, like how we can now do NHWC conversion at runtime, which is not mobile specific, but we ran into this on mobile. It's used when you have a kernel implementation that prefers a specific layout, for example, running on ARM or using NNAPI. The converter is aware of the layout-sensitive operators and can replace nodes using them with an NHWC version. Internally, it does this by wrapping the appropriate nodes with transpose operators, and then, thanks to our transpose optimizer, it then removes any transposes that effectively cancel each other out. We tested this using a production model that uses our new XNN pack support, which uses NHWC, and the input was also NHWC since the model came from TensorFlow, and all of the added transpose ops canceled out, including the initial input transpose. Ideally, this is what typically happens. For C# users, they can use ONNX Runtime in cross-platform apps, including apps targeting Android and iOS. We currently support Xamarin and are adding .NET 6 MAUI support in the next release. Fingers crossed. This will be a very interesting thing for C# developers on mobile platforms. We also added Android and iOS packages with the full ONNX Runtime builds. This will make it simpler for users getting started using ONNX Runtime in mobile scenarios. They can use ONNX models, and all offsets operators types that ONNX Runtime supports are included. It has a larger binary size, but this probably isn't an issue for most users as it's still relatively small. To give an idea, a minimal build that only includes necessary ops might be around 2.5 megabytes, and the full build is around 8 megabytes. ONNX Runtime Web is one of our newest offerings as we've seen growing interest in directly running inferences in the browser. We used to have a side project called ONNX.js, but this wasn't ideal. We needed to maintain two separate versions of the code, a JavaScript one and the primary C++ one, and we needed to ensure that the behavior was identical. Now we just compile the main C++ code into WebAssembly so that the ONNX Runtime Web is backed by the same core code base. As a bonus, it's faster, it uses less memory, and the resulting binary is smaller, basically like having another target architecture to compile for. Another big achievement for all of our JavaScript users is that we introduced a JavaScript library called ONNX Runtime Common, which has multiple backend implementations, Web, Node.js, and React Native, but one single common API. This allows the same JavaScript code to run on all the main web platforms. We also added XNN pack library support, and if the performance is good enough, we'll have OpenGL support in the upcoming 1.12 release. Challenges with data pre- and post-processing has been a recurring hurdle. We also recognize that custom operators used with ONNX Runtime that weren't officially in the ONNX spec could be shared. This led us to create ONNX Runtime Extensions, which is a library of shareable custom ops that can be built and run with the core ONNX Runtime operators. These are currently focused on model pre-post-processing work. The user no longer has to implement this in an outside language. It can be done entirely inside the model run call. It has things like text conversions, for example, changing strings into uppercase, lowercase, math functions like splitting positive and negative values into separate tensors, etc. Currently, the ops in the library are mainly focused on NLP, natural language processing, vision, and text domains, which present some of the most challenging data processing steps. But we expect this to evolve as new needs are identified. There are flexible build options for it, like having it be a part of the ONNX Runtime library through the static library build option. It's currently being used by our internal partners in the Microsoft Office team.